Welcome to massive open online course on basic principles and calculations in chemical engineering. So, we are discussing about the basic principles of multi-phase systems under the module 5. Now, in this module, today's lecture will be on process of phase change, basically for the process of condensation and vaporization and their calculations. In the previous lecture, we have described about the equilibrium laws like Raoult's law, Henry's law, even principles of humidity and saturation there, and based on which we have obtained how to find out the dew point temperature, even saturation temperature, even humid volume, how to calculate the that moisture content in the open atmosphere, and also from the psychometric chart how to how to actually estimate, or you can say find out their humid volume, even in dew point, and also relative saturation. All those things we have discussed in the previous lecture. So, in this lecture the further extension on that equilibrium condition, basically for the condensation and vaporization process, and in this case since you will see that phase will be changing from one phase to the another phase. So, phase transition of matter is that is related to this topics, like that different states of the materials that will be called as phase also. So, in that case solid, liquid, gas and plasma, all those are different state, and from this state or from this phase that will be converted into another phase or state, like here that solid can be converted to a liquid after melting, and solid may be converted into gas by sublimation process. Even liquid you will see that it will be converting into solid state after freezing. Even liquid can be converted into vapor after vaporization process, and gas may be converted into solid after deposition, and it may be converted into the state of liquid after condensation. Also this gas of course sometimes to be converted into plasma state by ionization process. But from the ionization condition or plasma state condition, it may be converted to gas by recombination process. So, these are the different that phase transition process here. So, that is that called that freezing, deposition, condensation, sublimation, vaporization, recombination, ionization. So, these are the different processes. In this lecture mainly we will focus on the that condensation and also vaporization process. So, what is condensation? We have already described this condensation basically is the conversion of the physical state of matter from the gas phase into the liquid phase, and it is also called that inverse vaporization, that may be that vapor to converting into liquid phase. So, that is why it is also called that inverse vaporization. It is also be defined as the change in the state of water vapor to liquid water when it contact with a liquid or that solid surface there. So, this is basically condensation process, and that we have described that psychometry principles and also chart. Their psychometry that measures the rate of condensation through evaporation into the air moisture at various atmospheric pressures and temperatures. And in this case you will see that water is the product of its vapor condensation. Condensation is the process of such this phase conversion. It is an important component of that distillation process, where that sometimes vapor component that is coming out from the distillation column, it will be condensed to a liquid phase, and again it will be sent to the distillation column as a liquid phase, and some portion of that liquid phase will be further processed for useful product. It is also important in power generation, water desalination process, thermal management, refrigeration process and air conditioning process. So, all those processes basically involve with this condensation process. Now, before going to that calculation, you have to know that what will be the partial condensation. Basically, this is that the mechanism by which that that matter will be partly condenses into a vapor stream, and in that case partial condensers generally being used, and it will have the characteristics like feed stream contains only condensable vapor components, and also it will have some exist streams that will contain the liquid and vapor which are in equilibrium. So, condensation is caused by cooling or that increasing pressure, and liquid and vapor that emerging from the partial condenser are separated using a flash separator. So, here you will see that that liquid and vapor emerging from the partial condenser are separated using a flash separator here, and in that case you will see that your vapor and liquid will be coming after flash separation or flash vaporization process. Now, how to do that material balance on the condensation? In this case you have to note it down that if you know the dew point of water, we have already described that how to find out the dew point from the psychometric chart, where that partial pressure will be equal to vapor pressure of the gaseous component or any matter or any that components. So, in that case if you know that dew point of that water in a gas, you can estimate that partial pressure of the water vapor in a gas. And also when a partially saturated gas is cooled at constant pressure, as in the cooling of air containing some water vapor at atmospheric pressure, you will see that the volume of the mixture may change slightly, but the mole fractions of the gas and water vapor remain constant until the dew point is reached there. So, at this point water begins to condense, that is at that dew point, and the gas remains saturated as the temperature is lowered there. So, this is to be remembered before going to do the material balance on condensation. Let us have an example for this condensation process. Here in this case you will see that if suppose in winter season in a day it is seen that atmosphere at evening is at 30 degrees Celsius and 80% relative humidity at a pressure of 0.96 atmospheric pressure. But condition is changed at night. Naturally it is happening during the period of winter, and it is seen that the temperature at that night is 20 degrees Celsius at that 0.98 atmospheric pressure. Now, you will see that here important that relative humidity at 80% at 30 degrees Celsius where pressure is 0.96, but at the night you will see that the temperature is lowering to 20 degrees Celsius, whereas atmospheric pressure also will be increased there 0.98 atmosphere. Now, because of this temperature and pressure change, there is a deposition of water as a dew at night. Now, at this condition you have to find out what should be the percentage of the water in the afternoon air per mole of air. You have to calculate which is deposited as dew at that night. Basically, you have to find out what will be the amount of that is water in percentage that is condensed as a dew at that night. Here in this case simply that your temperature is lowering, pressure is increasing, relative humidity that at the day but what will be the relative humidity at night, that also you do not know, but let us see how to calculate these things, that how much water is actually condensing as a dew at night at that particular condition. Now, in this case we have to consider that this is a closed system that reaches equilibrium there. In this case, if we draw the schematic diagram, suppose in day this amount is dry air and here water vapor will be there. So, dry air contains this water vapor at the temperature 30 degree Celsius and pressure is 0.96 atmosphere, whereas at night you will see that this that amount of vapor will be that lowered at that night after condensing out as a liquid, that amount is W. And at night that condition is pressure is 0.98 atmosphere and temperature is 20 degree Celsius. So, this is your problem. In this case, what will be the amount of water that is condensed as a dew at night, that you have to find out. Now, as a solution, what we can say that first of all you have to find out what should be the vapor pressure of the water at 30 degree Celsius. So, this vapor pressure of water at 30 degree Celsius, it is that given here 31.8 millimeter mercury, that is in atmosphere 0.042. Whereas, this vapor pressure of water at night, that is at 20 degree Celsius, this will be equal to 17.5 millimeter mercury, that will be 0.023 atmosphere. Now, the partial pressure of the water in the day air, that will be equal to what? 31.8 millimeter mercury into 0.8, because 0.8 is the relative humidity. This relative humidity basically that ratio of ratio of what is that that means here partial pressure to the vapor pressure. So, from which you can say that what should be the partial pressure of the water, that will be simply that 31.8, this is vapor pressure into humidity. So, it will be coming as 25.44 millimeter mercury, it is around 0.033 atmospheric pressure. Now, in this case this implies that dew point temperature will be 27 degree Celsius. So, at this partial pressure at in the day, that here in this case at this particular partial pressure, it is seen that this the dew point temperature will be 27 degree Celsius. Okay. From this because you can get also some from that 20 degree Celsius or 30 degree Celsius at that day condition. From this psychometric chart, if you go to that 80% relative humidity, and from that what should be the dew point, that if you go to that up to that 100% saturation, it is seen that dew point will be equal to 27 degree Celsius at 80% relative humidity at 30 degree Celsius. So, from this psychometric chart you can calculate here what should be the dew point there. Now, consequently you can say that water does condense from the air as it cools. Now, we need to get the compositions of the dry and night composition of the day and night air. So, we can carry out a material balance there. You then calculate the partial pressures in the day and night streams, and the result of which in effect will give the composition of the two streams. So, here we know that total pressure will be equal to what? Partial pressure of air and partial pressure of water vapor. Now, at day, so we can say that partial pressure will be equal to here total pressure is given 0.96, whereas partial pressure of water at day 0.033 we have already calculated, and then it will be finally after subtraction from the total pressure, then partial pressure of air will be equal to 0.927. And then at night also what should be the partial pressure of water, that also can be calculated from this total pressure by subtracting the water partial pressure. So, it will be coming as 0.98 minus 0.023, then it will be coming as 0.957 atmosphere. Now, from this we can say that moles of water at night by moles of dry air, that will be equal to partial pressure of water at night by partial pressure of dry air. So, that will be equal to here 0.023 into divided by 0.957, that will be 0.024. Similarly, moles of water at night, that will be equal to then 0.024 into 1 moles of dry air, then it will be as 0.024 moles there. and then moles of water a day by moles of dry air, that will be equal to partial pressure of water at a day divided by partial pressure of dry air there, then it will be coming as here 0.036, and therefore moles of water a day, it will be as what is that 0.036 into 1 mole of dry air, then it will be coming as 0.036 moles. So, moles of water that is deposited at night, it will be what is that, simply this is your that daytime, and this water moles is at night time is this here. So, if you subtract this 0.024 moles at night from the water moles of the day, that is from 0.036, then you can get this that here 0.012 moles of water deposited at night. So, this will actually will be coming out as a DO at night. Now, percentage of water in that day air then deposited as a DO, that will be equal to 0.012 this amount divided by what will be the that amount of that moles of water in the day. So, it will be coming as here like this. So, it will be around 33.33%. So, in this way you can calculate that what will be the amount of water that is deposited as a dew at night there. Let us do another example here. Now, drying process by condensing out of water. In this case, a gas stream containing 40% oxygen, 40% hydrogen, and 20% water in mole is to be dried by cooling the stream and condensing out the water. If 100 mole per hour of a gas stream is to be processed, what is the rate at which the water will be condensed out, and what is the composition of the dry gas? So, very simple that you have to draw first that schematic diagram here. It is shown in the slide that a gas stream of 100 mole per hour is flowing through that dryer. In this case here composition of the feed stream is 40% oxygen, 40% hydrogen, 20% water vapor. Now, we have to that is to be dried by this cooling the stream and condensing out the water. Now, you will see that at this stream 2, this condensate will come out as amount C, where water will be 100%, no other composition will be there, like oxygen, hydrogen will not be there. But the dry gas, it will be containing oxygen, some mole fraction, that is X O2, and also hydrogen, that will be 1 minus X O2 3. So, dried gas amount is D, it is not known to you. So, based on this problem you have to find out what is the rate at which that water will be condensed out and what is the composition of the dry gas there. Now, let us do this example here to solve. Now, let us consider this basis is 100 mole per hour, that wet gas here with the composition of 40% oxygen, 40% hydrogen and 20% water, and consider the overall total material balance and that component balances and also component balances here, like here 2 component balances. Here first of all you have to do the total material balance, like 100 will be equal to D plus C, because this is input, these are output. So, 100 will be equal to D plus C, and component balance for water, all water in the feed is here condensed. So, we can say that 0.2 into 100, that will be coming as C, and so we can say that 100 into 0.2, it will be that simply that 20 mole of water as a condensed. So, C will be equal to 0.2 into 100, that will be equal to 20. Similarly, if we do the component balance for oxygen, then you can see that 40% of oxygen in the feed, that is 0.4 into 100, that will be exactly equals to the outlet oxygen contents, that will be here in this stream 3, that will be that then D into XO2 here, sorry, this 3 will not be here, this is in suffix. So, it will be basically that XO2 in the stream 3, then it will be coming as XO3 into D. So, by solving we can say that D will be equal to 80 mole per hour, and XO2 3 then it will be coming as 0.5. So, once you know that XO2 at 3, then here XO2 at stream 3, that is equal to 0.5. So, similarly, so we can say that at this stream hydrogen will be equal to X hydrogen at stream 3, it will be coming as 1 minus 0.5, that will be equal to 0.5. So, this is your mole fraction of hydrogen in stream 3. So, in dry gas, of course, that amount D, what is amount 80 mole per hour, will contains that 50% oxygen and 50% hydrogen there. So, in this way you can do that material balance, and in this case total material balance and also component material balance to be done, and how much water will be condensed, you can get it from this material balance. Next we will go for that vaporization process. What is that vaporization? This vaporization basically caused by that reducing the pressure or by heating. Vapor and liquid streams are in equilibrium there. Now, to calculate that amount of the respective vapor and liquid phases that evolve at equilibrium condition, when a liquid of known composition flushes in a flash evaporator or flash vaporizer, it is called flash vaporization at a known temperature and pressure. You must use that use the following equation of an equilibrium constant of K I together with a material balance. So, in this case at equilibrium condition of that vaporization condition, you will see that vapor and liquid will be in that equilibrium condition at this vaporization condition, and at this flash vaporization you will see that at equilibrium condition some amount of vapor will be there from the top of that flash vaporizer, and from the bottom there will be liquid will be there. Now, at that condition vapor and liquid will be in equilibrium, and the composition there will be that in the vapor, let it be considered as Y I for that component, and that in liquid phase that composition will be X I. So, at equilibrium condition you will see that this composition in Y I, that is in vapor, that will be equal to that mole fraction of liquid just by that just adjusting with some equilibrium constant. So, here we can say that if suppose Y I the mole fraction of component I in the vapor phase, and at that equilibrium condition with the mole fraction of I, if it is equilibrium in condition, then we can write Y I will be equal to some K I into X I. So, in this case this Y I is equal to K I X I. From this we can write here K I will be equal to Y I by X I. This K I is called that equilibrium constant for the component I, and this since it is mole fraction at that equilibrium condition. So, in the vapor phase that pressure will be of that component I will be vapor pressure at that equilibrium condition, and that what will be that total pressure of the system, from which you can calculate what should be the equilibrium condition or equilibrium constant. Now, in this case this K I you can calculate also from that if you know that reduced temperature and also that critical pressure there, and from that you can calculate this equilibrium constant from this correlation suggested by Sandler, this empirical equation. In this case this empirical equation will be valid only if your that ratio of critical temperature to the total pressure sorry critical temperature to the temperature of the system is greater than 1.2. So, you can directly use this correlation to find out this equilibrium constant. Otherwise the equilibrium constant you can find out from the table that is given in your textbook in the appendix. You can find it out what would the equilibrium constant there. Now, you have to remember that at xi is equal to 1 there, that means that here partial pressure will be equal to vapor pressure there. So, you have to that remember for 100% of molecules of that component I in the liquid phase, then there will be a partial pressure of that vapor pressure will be equal there. Now, calculating that related equilibrium vapor liquid composition, what you have to do? First of all, you have to calculate the bubble point temperature of the liquid mixture that is given at the total pressure and liquid composition. So, you have to know first that bubble point temperature, that means at which temperature this that that mixture is exist and also it is supplied for further processing, that can be considered as bubble point temperature, and also at that bubble point temperature what is the pressure and liquid composition there. Now, calculate the dew point temperature of a vapor mixture given that total pressure and vapor composition. Also, you have to calculate the related equilibrium vapor liquid compositions over the range of mole fractions of 0 to 1 as a function of temperature that is given at that particular total pressure. Then you have to calculate the composition of the vapor and liquid streams and their respective quantities when a liquid of given composition is partly vaporized, that is called flash vaporization at a given temperature and pressure. In this case, the temperature must lie between the bubble and dew point temperature of the feed. Now, method to calculate the bubble point temperature and pressure, how to calculate that bubble point temperature here, we will describe that here. To calculate that bubble point temperature at a given total pressure and liquid composition, you have to solve this equation like this. Always you have to know that at that equilibrium condition in the vapor composition and the that liquid composition, you will see that summation of that composition will be equal to 1. That means here summation of yi will be equals to 1. So, at which condition, at what temperature, you will see that the summation of this mole fraction of the components in the vapor phase will be equals to 1. So, at that condition it will be given, it will be their respective temperature of that bubble point temperature. So, here if I substitute here yi as kixi, so we can say that summation of kixi will be equal to 1. Here also in this way you can calculate that at which condition you can get the summation of this ki into xi will be equal to 1. So, respective temperature will be called as that bubble point temperature. Now, these ki's are function of solely that temperature, and because each of the ki's increases with temperature there. For an ideal solution, it can be written as that this total pressure will be equal to what? A summation of this that PIV into xi, that means partial pressure of that components in the mixture. So, summation of that partial pressure can be calculated from the vapor pressure at that equilibrium condition. That is why the summation of this vapor pressure into mole fraction at that particular equilibrium condition will be equals to total pressure. So, that if you are getting that total pressure will be equal to the summation of vapor pressure into mole fraction, then you can say that at that particular condition the temperature will be that is called bubble point temperature. Now, once that bubble point temperature is determined, the vapor composition can be calculated from the relationship here y I will be equal to this is called partial pressure at that equilibrium condition, that is PIV into XI as per Raoult's law, and what will be the total pressure there. So, from this equation you can easily calculate what will be the vapor composition at that particular bubble point temperature. Now, let us do an example based on this concept. Now, in this case suppose a liquid mixture containing 5% normal hexane and 95% normal octane is to be vaporized in a flash vaporizer. Now, you have to find out what should be the composition of the vapor formed if the total pressure will be 1 atmosphere, and what is the bubble point temperature to vaporize that liquid at its equilibrium condition with the vapor. Now, in this case you need to calculate the vapor pressure of the components I. Now, for that you have to use that Antony's equation, but at which temperature this that vapor pressure to be calculated, that is not known to you. So, you have to keep that temperature certain temperature, like that if it is denoted by T, then keep it as T, and that at that temperature you have to find out what should be the vapor pressure by this Antony's equation. Now, to calculate that vapor pressure by Antony's equation, you need to sum Antony's constant. So, it is given here for the component for normal hexane, this Antony's constant is given here, and for normal octane also this Antony's constants are given in this table as shown here in the slide. Now, we need to solve this following equation to get that bubble point temperature based on this problem. Now, we know that that to get this bubble point temperature, your equilibrium condition will give you this equality of that total pressure will be equal to summation of that is PIV into XI. So, for all components in the mixture you have to sum up this product of this partial pressure of that component into its mole fraction. So, after that what will happen? Now, let us see here here since total pressure is given to 1 atmosphere, that is 760 millimeter mercury, and here in this case this vapor pressure of that components will be there considered. So, first of all, this since it is I component, I is here it is 2 components because only hexane and octane are there. So, for hexane we will use this notation H. So, here 760 will be equal to then Pi HV for hexane into Xi H for hexane, and similarly for that octane also we can write here POV and that XO there. O for octane, H for hexane. So, here if you substitute this value for vapor pressure for hexane and octane, what is the vapor pressure of hexane here as per Antony's equation, exponent of A minus B by C plus T. This is your Antony's equation for vapor pressure of that component that for hexane, and similarly component of hexane is Xi, and again if you substitute that equation for vapor pressure for octane, and then if you multiply it composition as x0, you can simply express by this equation based on that total pressure and vapor pressure. Now, substitution of this A, B and C and then solving the equation for T, what it will come? You can get that T will be equal to 392.2 Kelvin, which is a bubble point temperature. So, from this equation you can easily calculate this bubble point temperature. So, here you need to know that only that Antoine's equation and also vapor pressure at that particular temperature, that solving this equality of this total pressure with this that summation of this vapor pressure into its components, then you can get easily what will be the bubble point temperature. Now, at this bubble point temperature, as per Antoine's equation, you have to find out first what will be the vapor pressure of hexane and what will be the vapor pressure of octane, and it is coming as 150.0 millimeter mercury for hexane and 607.65 millimeter mercury for octane at that bubble point temperature of 392.2 Kelvin. After that, you have to find out what will be the vapor phase composition of here hexane. So, hexane Y hexane can be calculated from this equation here, P is V X is by P T. Then you can easily calculate what should be the composition here. It is coming 0.2, that is 20% of hexane, and remaining will be your octane, that will be 80% there. So, in this way you can solve for bubble point temperature and also vapor composition when a liquid mixture will be partially vaporized in a vaporizer. Similarly, you can calculate that what should be the bubble point pressure also. Now, in this case you will see that a liquid mixture that contains 50% pentane and 30% hexane and remaining, that is 20% cyclohexane, all in mole percent, that is x1 is equal to 0.5, x2 is equal to 0.3, x3 is equal to 0.2. Now, at this temperature of 400 K, the pressure is gradually decreased. What is the bubble pressure and composition of the first vapor that is formed there? Now, assume that ideal liquid mixture and ideal gas there, and it will follow that Raoult's law. So, here in this case, instead of bubble point temperature, you have to find out what will be the bubble point pressure. Now, in this case, first of all you have to calculate vapor pressure of each component at 400 K by Antoine's equation. So, this will be your that here it is given the for component 1 this vapor pressure is here, and for component 2 it is given, and for component 3 it is given. Now, at the bubble point the liquid phase composition is given, so that partial pressure of each component is as like this. So, partial pressure will be calculated based on this equation. You know that vapor pressure of each components by the Antoine's equation, then you can get that partial pressure of each component P1, P2, P3 respectively. So, from which you can easily calculate what should be the mole fraction of, in the vapor based on this partial pressure. Then you can get this mole fraction of each component as Y1, Y2, Y3 here shown in the slide. So, the bubble pressure will be equal to here, what is the total pressure will be there, that will be equal to summation of all partial pressure of that components 1, 2 and 3. So, it will be coming as 7.189. So, it will be called as bubble pressure. So, in this example you practice it, and you can that have idea how to calculate that bubble point pressure. Similarly, how to calculate that dew point temperature here. This is also reverse that vaporization to the condensation. So, in this case, to calculate the dew point temperature at a given total pressure and vapor composition at equilibrium condition, you have to solve the equation here, that summation of xi will be equal to 1, and also you can say that from that relationship of equilibrium y is equal to yi is equal to ki xi. From that you can write after simplification as summation of yi by ki will be equals to 1. Now, for an ideal solution we can say that this summation of this will be equal to 1. So, from this here we can say that respective temperature at which this equality satisfy will be called as dew point temperature. So, in selecting a particular form of the equation to be used for phase equilibria calculations, you must select a method of solving that equation that has desirable convergence characteristics to the. Now, how to calculate that dew point temperature accordingly, like as per the same problem given in previous example, like a vapor mixer contains 50% pentane, 30% hexane and 20% cyclohexane, where Y1, Y2, Y3, X3 is given to you, and at pressure 5 bar the temperature is gradually increased, and what is the dew point temperature and the composition of the first liquid that is formed, and assume ideal liquid mixture and ideal gas law. So, in this case also here pressure and composition of that component I are given, and also provides the equation that follows an implicit equation for that temperature which needs to be solved numerically here. So, in this case summation of xi, that means summation of Pt into yi by Piv, that should be equal to 1. Now, in this case when this that at which temperature you can get this equality is equal to 1, after substitution of Antony's equation you will see that you have to solve for temperature T, and then it is coming 393.3 K. So, this is your that that dew point temperature. Now, in this case this xi then can be obtained as from this relationship, and which will give you that respective composition for that components 1, 2 and 3. In this way you can calculate this dew point temperature. Similarly, we can also calculate the dew point pressure. In this case the same mixture of 50% pentane, 30% hexane and 20% cyclohexane with this composition at 400 Kelvin temperature, the pressure is gradually increased, and what is the dew point pressure and the composition of the first liquid that is formed, that you have to find out. So, in this case again this equality to be followed, that is Pt into summation of yi by Piv, that will be equal to 1. So, in this case vapor pressure at 400 K by Antony's equation are here calculated as like this for component 1, 2 and 3 respectively. So, from those you can easily calculate what should be the mole fraction of those components once you know that vapor pressure. So, from this vapor pressure of components 1, 2 and 3 you can calculate what should be this value of 1 by Pt, that will be as per this equation here, okay. And then this after substitution of this yi and Piv, they are then you can easily calculate what should be the that total pressure there. So, it is coming here like this, here 0.1729, and which will imply you that total pressure will be equal to 5.78 bar. Flash vaporization with vapor and liquid in equilibrium, that we have already discussed, that at that flash vaporization condition, that Ki will be equal to yi by xi, that will be Pi by Pt, from which you can calculate that what is the partial pressure, what will be the total pressure, what should be the temperature at which that vapor will be condensing or a liquid will be vaporized there. So, to calculate that amount of respective vapor and liquid phase that evolve at equilibrium, when a liquid of known composition flashes in flash vaporization at a known temperature and pressure, you must use that equation that will follows together with a material balance. Now, material balance in the flash vaporization to be done based on this. Suppose there is a flash vaporizer, and in this vaporizer the liquid feed is coming with some composition, and at that vaporization process you will see that some amount of vapor will be coming out from the top of this vaporizer, and some amount will be coming out from the bottom as a liquid with composition at a known total pressure and temperature. Now, in this case what will be the feed amount and what will be the vapor amount and also liquid amount after vaporization, then it is if it is not known to you, then you have to do the material balance once that is provided at least one variables there. So, based on that, if we do the total material balance for this vaporizer, we can write simply F will be equal to L plus V. And also if you do the component material balance, we can write for component I in this way, that Fxf I, that will be equal to Lxi plus Vyi. Since we at equilibrium condition we know that yi is equal to Ki into Xi, so we can write this equation of this component material balance after substitution of this yi will be equals to ki xi here, then finally you can write here f x f I will be equal to L into yi by ki plus b into yi at this equation. Now you will see that from this equation we can simply express that what will be the yi will be equal to, that is here after rearrangement you can get it, or you can express this in terms of here like this x f I by 1 minus L by f into 1 minus 1 by ki. So in this case if you know this yi and also at equilibrium condition in the vapor phase all the components composition will sum up to 1, then you can say the summation of yi is equal to 1. So if you substitute that yi from this material balance equation, and you can then express like this here as shown here in this slide that equation, and here in this case you can write the summation of x f I by 1 minus L by f into 1 minus 1 by ki, that should be equal to 1. So here L by f is unknown to you, what will be the amount of liquid and what will be the amount of f, it is not known to you, but if you know that vapor composition, amount of vapor composition, then you can calculate what will be the f and L, or what will be the L by f also you can calculate from the material balance, or f is given to you, what should be the V and L, that also you can calculate. Okay. So in this case very interesting that this equation as shown here L by f, if you keep on changing that L and f value and also respective you calculate that summation of this terms here, you will see that at a particular liquid and that is L and f value, you will see that the summation will tends to becoming 1. So at that particular condition your value of liquid and feed amount will be known, and that condition also you can say that what will be the composition there. So according to that you can have that what will be the composition in the vapor phase and liquid phase. So this is basically depending on that material balance overall. So let us do an example based on this material balance of this flush vaporizer. Now you know that during that ammonia synthesis from nitrogen and hydrogen, the products are cooled and separated in a partial condenser that is operated at minus 33.33 degree Celsius and 138 bar absolute as shown in figure below here in the slide. Now calculate the composition of the vapor and liquid streams. In this case consider that 100 mole of feed is processed for the synthesis. Now here F is given to you, and the compositions are nitrogen, hydrogen, ammonia, air, methane as per figure, and in the vapor composition as you know that if I denote that composition as 1, 2, 3 for that respective nitrogen, hydrogen, ammonia, air and methane. Then in the vapor phase what will be the composition, it is not known to you, also what will be the total amount of vapor, it is also not known to you, that you have to find out. Similarly in the liquid phase the amount L is not known to you, and also composition for that respective components are not known to you, but equilibrium constants are given to you for nitrogen as like this, for hydrogen, for ammonia, for that argon and also for methane, these are given to you. So with these that parameters or that data you can find out what should be the composition of the vapor and liquid streams. First of all what you have to do, the total material balance. Now in equation number 1 it is shown that this material balance will be as 100 will be equal to V plus L, because F will be equal to V plus L. That means here input will be equal to total output, that is material balance concept. So it will be coming as 100, that will be equal to V plus L. Now after that you have to do the component material balances for each component, like this for nitrogen what will be the component material balance? You can do it 100 into 0.22. This composition is given in the feed phase there. So, and in the outlet phase it is not given, it is our assumed that it will be y1 and x1. Similarly for other components also, for hydrogen this is your material balance, for ammonia this is your material balance, for argon this is your material balance, and methane also this is your material balance. So, for nitrogen to methane, this material balance equations are given from equation number 2 to 6 here in the slide. Now, next you have to do the summation of these mole fractions in the vapor phase and liquid phase. In the vapor phase, summation of the vapor phase composition will be equal to 1, and also summation of the liquid phase composition will be equal to 1. Now, at equilibrium conditions, you know that yi will be equal to ki xi. We know that yi will be equal to ki xi, that is at equilibrium condition. Now, based on this equilibrium equation, you have to express for each component what will be that equilibrium equation. For nitrogens, here it is given y1, that will be equal to 66.67 into x1. Here 66.67 is the equilibrium constants for this nitrogen. Similarly, for other components you can find out that hydrogen, for hydrogen it will be y2 equals to 15 to x2. Similarly, for ammonia, similarly for argon, similarly for methane, what will be the equilibrium relations or equations there. So, it can be expressed by this equation number 9 to 13 for respective components of nitrogen to the methane as shown in the slides. Next, you have to express this equation 2 to 6 by rearranging it. What should be the mole fraction of x1, what should be the mole fraction of y1, what should be the x2, what should be the y2, similarly x3, y3, similarly x4, y4, and also x5, y5. So, by this equation number 14 to 18, you can express what should be the mole fraction of each components based on that material balance by unknown values of liquid composition and vapor composition. Also unknown amount of liquid and vapor there. So, by this respective that equation from 14 to 18, we can that rearrange these things as here like this with that equation number 9, that equilibrium relations. We can get that equation here for component 1 in the liquid phase and component 1 in the vapor phase. Similarly, for component 2 it can be written, and similarly for component 3 these are can be written for component 4 and component 5 like this. Now, you will see that all this liquid phase composition for all components, if you sum it up, it will be coming as 1. And also similarly, if you consider that here vapor phase composition, then summation of yi will be equal to 1. So, either one you can consider at a particular vapor amount and liquid amount, then when that ratio of liquid and vapor will give you that summation of this xi will be equal to 1, or yi will be equal to summation of yi will be equal to 1. So, based on this you can say that at a particular, you will see that vapor and liquid amount, this summation of this yi and summation of xi will be equal to 1. Now, by trial and error method, just by changing of your liquid amount and vapor amount, and once you will see that this summation will come to approximately 1. You cannot say that it will be 100% 1, but there will be very least error to get this 1 value. That means maybe 1.0001 or 0.9999 like this. So, when it will come, that means near about 1, you can say that at that particular vapor and liquid amount will give you this equality of the summation of xi or summation of y will be equal to 1. Now, once it is finalized for this that liquid and vapor amount, here you can say that this at this amount we can say what should be that vapor composition and that liquid composition for all components here, for nitrogen and for hydrogen and for ammonia, argon and also methane there. So, you can find out there respectively just by putting that value of that liquid and vapor amount in the respective equation here in this equation number 14 to 18 there. So, in this way you can calculate what should be that liquid and vapor amount by this flash vaporization condition in a vaporizer with this material balance. So, I think you understood that how to solve that vapor composition and liquid composition to find out at a particular that temperature and pressure by this material balance. Also at an equilibrium condition, how to calculate the vapor composition, liquid composition from its vapor pressure or that from the that dew point temperature or bubble point temperature. Also you have, I think understood that how to find out that dew point temperature, how to find out that bubble point temperature just by calculating the vapor pressure by Antoine's equation and substituting it to the equality at that equilibrium condition of total pressure will be equal to summation of partial pressure of the components, and then partial pressure will be related to that vapor pressure there. So, accordingly you can calculate what would be the dew point, what would be the vapor bubble point temperature based on that vapor pressure. So, I think I should suggest you to go further that some example that is given in your textbook, and also more about this flash vaporization. You can get it more information from this textbook and also reference books there. In the next class we will describe regarding the principles of energy and also we will start that new module there, and under that principles energy, how to do that material balance for energy, and also some that different forms of energy and how it can be used to calculate that material balance, and where that this energy balance will be required, we will be discussing in the next lecture. So, thank you for your attention.